So start the lecture. So welcome back, everyone. Thanks for still making it a lecture or watching online. After it's posted, so we're getting close to the end of the great. Through the end of the semester, and we're going to be talking about clustering today. And so this lecture will be kind of our main algorithm on clustering. We're going to talk about Lloyd's algorithm, which is the kind of the most typical algorithm to solve the kMeans clustering problem formulation, which is the most common clustering way of posing the clustering problem. And also most aligns with the rest of how we talk about stuff in the class. We'll see in the next lecture on Wednesday that there are completely different ways to think about clustering. I'll give you a little taste of one. I'll also give you one that kind of ties back into the statistical formulation going on. Okay, but today will be Lloyd's algorithm, which will be the main algorithm for how to actually find this clustering. Okay, so let's look at the schedule. We had one lecture so far on clustering that kind of introduced the concept and talked about these Voronoi diagrams, which is needed to map points onto the clustering center. And then tomorrow we'll do one more lecture, and then we'll go into classification, which will be the last section of the class. There's a question, is clustering going to be on the quiz? Okay, so quiz 5 is today, the second to last quiz. Quiz 5 will only cover dimensionality reduction. It'll just cover the lectures. I don't know if I can, from here up through here, right? So these 4 lectures is just going to cover these topics. So we shifted stuff around this, and because of election day, so we're just going to cover those topics. All of clustering and part of classification will go in. Will go into the next quiz, but this is what quiz number 5 is going to be on. As usual, it'll open at 2:30, and I'll stop the lecture then. You're allowed 1 sheet of paper, and you can turn that in for up to 5 points of bonus credit as a cheat sheet. Okay, great. Oh, all right. Thank you. Okay. Okay, and then homework 4 is also due on Wednesday. Hopefully you've all started on that. If you haven't, this homework features probably the most kind of challenging kind of programming aspect you will have in the course. You're going to put together the ideas from gradient descent and linear regression. You're going to solve linear regression using gradient descent. There are other ways to solve it. You don't need to solve it this way in general, but this is how most of machine learning works. And so you're going to implement kind of the simplest bare-bone versions of this, but this is kind of like a real primer into the whole thing. And so you'll be much more prepared for when you take the machine learning course by having done this. That being said, it deviates a bit more from all of the pieces of code I've showed you before. So you have 2 days left to do it. Don't wait until the last day to do it. So if you haven't started yet, start soon, because this one might take a little bit longer. It'll also have some dimensionality reduction content on this homework. Hopefully that part is mostly pretty straightforward once you get it, and should reinforce those ideas pretty well. We're going to get the last homework out, homework 5, hopefully maybe by the end of this week. That'll be on some clustering, some classification. It'll have little or no kind of programming aspect to it. So this homework should be a little bit lighter in that way. And I hope as you all kind of are racing to get through the end of the semester, this homework is not as much of a burden towards that. Still, don't wait till the last minute, but that will be out relatively soon. We've started kind of piecing that one together. So great. So any other questions on the schedule? And again, if you need review of Python. Oh, didn't mean to hit that. Review of Python. Hassan put together this nice tutorial about how to load files. And so great, there's a lot of great information in there. Thank you again, Hassan. Will you be allowed cheat sheet on the final? Yeah, so my idea for the final is that you would be allowed a larger cheat sheet. I would say in the past I had done had 4 quizzes, and I allowed you to kind of use 4 sides of paper, so 2 sides front and back, or 4 sides all front. I might allow 6 pages because there's more content on there. You'll definitely be allowed a cheat sheet. Yeah, so what format we'll take will probably depend on whether we do it as a take-home piece of paper that you have to scan and send back in, or if it's going to be as a Canvas quiz. But yeah, you will also be allowed a cheat sheet on there. Yeah. So great. So okay, so let's get into the lecture. Again, if I seem to be rattling on and we've kind of crossed over around 2:30, please stop me so we can open up the quiz here. Okay. Great. So clustering. So remember, okay, so the kMeans clustering, and I want to say this is a formulation. Okay, so people might just say kMeans clustering, and that encompasses everything. But kMeans clustering is kind of a formulation about what I mean by clustering, and it's not an algorithm. We'll talk about the algorithm today, and this algorithm is called Lloyd's algorithm. Okay. So, and there are other algorithms other than Lloyd's algorithm, which is why it's useful to give this one a name. And so that is where we're given an input. We're given an input X, which is going to be a subset of RD. I'll think of these as endpoints. So X equals X1, X2 up to Xn. Okay, and we're given some K, which is going to be an element of so Z plus. So Hassan, how do you usually write this space of the integers? So it's it's a positive integer. So is in the set 1 to up to some value. It's some number of clusters, right? So this one's telling us the number of clusters, and we're going to be given this as an input. We're going to discuss at the end of this lecture how would you choose the value K. Some guidance on that, although it's not going to be kind of some like great kind of there's a cool trick you can use to always solve it. Is going to be a little just a little bit fuzzy. Okay, and so there's going to implicitly be that there's some distance in between the points. Goes the positive real numbers, and this distance between X1 and X2 is going to be exactly the Euclidean distance between them. Okay, so we're going to assume that distances are measured with Euclidean distance, and this again, remember, we have to that should mean that the coordinates kind of the data points align with each other, so it makes sense to take the Euclidean distance between them. We don't have like height and weight together in these things, and that might not make sense. Okay, so we're assuming that this is all part of the input, and now the goal is to find a set S of these of these sites, S1, S2 up to Sk, and these are also going to be a subset of Rd. And the goal is to find the to minimize so I'm going to sum a cost function over all of the points of the distance between xi, remember this is the Euclidean distance between xi and the mapping onto the closest center squared, right? And we remember that this is the maps xi to arg min sj in the set of the centers that minimizes the distance between xi and sj. So it's the closest center. So I map every point to its closest center, and this gave rise to this Voronoi diagram, which in low dimensions looks kind of simple, but in high dimensions gets really complicated. Okay, and it maps it to its closest center, and we want to minimize the sum of the squared distances, as we've done throughout this entire semester. There are other formulations that minimize kind of other distances, or completely other formulations we'll see on Wednesday that don't even look like this at all. But this is the most common one. Also on Wednesday, we'll get a statistical kind of way of thinking about this and slightly tweak the algorithm to solve that formulation slightly better, where we think about this as a maximum likelihood estimator. Okay. Okay, so this is the goal of k-means clustering. Okay, we want to find, we're going to be given a set of points. Might look like this. Okay, this would be our input set x, right, where this might be x1, x2, x3, x4, and then our goal is to find, so 3, say, sites. If k is equal to 3, S1, S2, S3, and then basically there's this Voronoi diagram structure here, which says I map every point onto its closest center, right? And I'm looking at all of these, so residuals, this residual would be R1, and I want to square all those and minimize the sum of those squares, right? So that's what the formulation is. I need to find these 3 sites. Okay, so would these algorithms be easily adapted to discrete data? So I think you're thinking of where maybe, so I think this question is referring to each of these data points, and we're thinking of these as real numbers. Okay, and then we're measuring, I said we're measuring the Euclidean distance between them, right? I'm enforcing that the distance is the Euclidean distance. You could think of these data as not being Euclidean vectors. They could be categorical values. And then I could have I'd probably have a different notion of distance. I wouldn't want to use the Euclidean distance here, probably. Right, I could maybe do it. Say if it's a binary value, if these things, or if that coordinate is the same or not, and I square these and I add them up, and I could do that. But there are other distances you would want to use in that case. Okay, so if I look at this distance and I change that distance, part of the Lloyd's algorithm we're going to use is going to break down if this is not going to be the Euclidean distance here. Now, the formulation could be similar. I could find some center representative items for each cluster, but you would typically use the k-medioids instead, which is where you then, the sites may not be elements. I might restrict that those are elements of the set. That avoids some issues like there's a binary value and I return a 0.63 as that coordinate. Otherwise, that might happen somehow. And that minimizes the sum of the distances, and that's more common in that case. But there are other things to do as well. There are also distances like like the Jacquard distance, which is between sets. So I could replace this Euclidean distance by a Jacquard distance between sets, and then you can again run various forms of clustering on top of that distance as well. If you're interested in that, take the data mining course in the spring, and it will spend kind of a good chunk, several weeks on discussing these variants of distances, when to use them on different sorts of data, with some examples based on text, and then how to do this within, how to map this into clustering and different types of clustering. Yeah, so, and if you look in the book, the book has a bunch of other topics about that we have not gone into in this course, just to kind of keep stuff on a little bit simpler foundation. Okay, but hopefully to answer your question, but if I interpret your question correct, that's a great question that we unfortunately don't have too much time to get into in this course. Okay, so that's a review of what the formulation is about. Let's talk about the algorithm, Lloyd's algorithm. So just a bit of history. Stuart Lloyd came up with this algorithm in 1957 when working at IBM Research, and it was for one-dimensional data. And if you imagine, he actually implemented in 1957. There weren't a lot of computers back then, but apparently couldn't quite complete his experiments, and then they upgraded his computer and the instruction set changed. This was programming in the 1950s. It was a lot harder than than nowadays, and he couldn't finish his experiments, so he just put this paper aside for 15 years until he finally published it in 1982, when they realized that this was actually a pretty powerful idea. He was using it for compressing data in signal processing for IBM, I believe, or I think maybe it was different research lab, but he was using an IBM computer, I guess. And it was in 1D, but kind of the basic algorithm works in higher dimensions as well, as long as you're using Euclidean distance here. Okay, so this is a tribute to Lloyd's algorithm. There are plenty of other algorithms for this that have stronger guarantees, but almost everyone uses Lloyd's algorithm for kMeans clustering. Often when you hear the term kMeans clustering algorithm, you're referring to this algorithm. Okay, so let me try and, I'll write down the algorithm. It's just a couple lines, and then we'll work through kind of some details about it and some of these examples. Okay, so so the first step is I'm going to initialize. So it's going to be an iterative algorithm, like gradient descent type algorithm, like the power method was iterative algorithm, but it's going to be a little bit more kind of, there's more underlying structure going on here. So I'm going to initialize k points, and usually you say S is going to be a subset of this data, right? We're given input data points X, and we'll choose some centers as a subset of these. How do we do this? So kind of arbitrarily, kind of think about it at random, or in some ways. We'll come back to this issue a little bit, but I'm not going to completely go into the story of the best way to initialize this data. Okay, and then it's going to be this iterative algorithm. So I'm going to repeat 2 steps. Okay, I'm going to repeat 2 steps, and these are going to converge towards a nice solution for the centers. So I'm starting with k arbitrary points of the input, and then I'm going to do 2 things to kind of update the location of those centers. And the argument is that's going to keep getting better and better. Okay, so the first one is for all of the data points. Okay, for each of the data point, I'm going to assign xi to a cluster set xi, right? So these centers, right? The output here is going to partition x into the union of j equals 1 to k of these xi, where each xi is going to have a, right, each of these is going to be some subset, or xj, it's going to be a subset of x, right? So I'm going to have the clusters are going to be these subsets of points that are kind of grouped together. And so I'm going to assign it to some xj. Let's call this xj. So phi of s of xi is going to equal sj. Okay, so basically what this is saying is I'm going to map every data point onto its closest point. Okay, so this is kind of implicit, right? If I look back at the cost function, the way I've written this here is kind of implicit, right? So this assignment here is kind of implicit because in the way it's measured, but I'm going to formally do this in the algorithm. I have to, in order to calculate the cost, I have to actually figure out what this mapping is. So let's make this explicit in the step A. Okay. And then step B is going to kind of ignore what the mapping is, but look at these sets. Okay. So what this is going to do is for all Sj in S, I'm going to update Sj is going to be equal to 1 over Xj, right? The size of Xj times, yeah, so it's going to be the average, okay? Right, so this is going to be equal to this is equal to the average point of each of these of this xj, right? So I look at all the points within each of the clusters, and I'm going to update this the site associated with that to its average, okay? And so at the end of last lecture, last Wednesday, we saw that if I know all the points and I want to find one center that minimizes the sum of squared distances, like we'd seen earlier in the semester in one dimension, this generalizes to d dimensions. And so if I know the cluster, I can pick the optimal site, right? So if I know the set of points, xj, that for one particular, that's one cluster, I can find the optimal site by taking its average. I can do that coordinate-wise average. So each coordinate, I take the average, and then I get d coordinates for the representation of the site. Okay, but this may have caused the closest, for every point, the closest center to have changed. So I have to go back to step A, right? So I can't just do one round of this. I have to do a bunch of rounds, right? So I'll go through an example, but this basically goes until, say, the set S is unchanged, or the change is so small. Okay, so this is now a discrete problem with the assignments. It's discretely assignment, so it will eventually stop, right? Unlike a gradient descent, it might not ever stop. It might just keep getting closer and closer. But towards the end, it might move a very small amount if you have a lot of data. So you might still have some threshold that if the change is small enough between the last step, then I could stop. Okay. So you can have some other termination condition, or I could say, let's run for 10 steps, 10 iterations of this. That's 10 or 20 is usually enough. Okay, so this is there's two fairly simple steps of the algorithm. I map every point to the closest center, and then when I know the assignment, I take the average. Okay, so let's maybe this makes sense, but it'll probably help to see kind of an example. So let's work out an example here, and we can go back and understand this part. Okay, so let's start with some data. Okay, let me try and draw an interesting example here. Okay, so let's start with this example, and let's do it with 4 centers. Okay, so make the centers, start with them red. Okay, so I'm going to pick these 4 centers. Let's call these S1. Actually, let me make this a little bit more interesting here. Okay, let's say S1, S2, S3, and S4. Okay, these are the 4 centers, okay, that I start with. I initialize. I didn't know how to initialize. Let's say I pick these, okay? And so I don't have any assignment yet. How do I do the assignment? I draw these Voronoi. Think of, I actually have a for loop that I check everything against the closest center. Okay, it looks something like this, right? And each of these Voronoi cells tells me how to assign each of these points, right? So I've got one cluster that's down in S2, that's in this middle. Everything in this region here is assigned to S2. Okay, so I get my assignment in this way, and I'm not going to draw the assignment because this is going to get too messy if I do that. But you should be able to see it from these Voronoi cells. Okay, and then I'm going to update the placement of the sites. Okay, so S3, now it doesn't need to be one of the data points. S3 will be the average of these points, and let's say S3 will be down here. S2 will be the average of these 4 points. This will be S2. S1 will be the average of, was about 10 points here, and looks like S1 will be up here, and S4 is going to be this spot right here. Okay, so I've updated the centers. This was step B. I assigned these new centers and the average of there. And if that was the right clustering assignment, then these would be the optimal centers. But now that I have these green set of centers, I can reassign the points, right? So I'm going to draw a new Voronoi diagram with these sites. Okay. It's going to look slightly different now. Like that, maybe. Okay. So this is the new Voronoi diagram with these new sites, and this gives me a different assignment of the points. Okay. Let's move to some pink points here. Okay, so S3 I think is doing good here. It's moved, it's slightly shifted. Now this is S3. It now has those 2 other points that crossed over this line of the Voronoi cell. And that looks like a pretty good center for that group of points down here. S1 has lost 1 point from its right side. So it's going to move slightly this way. This will be the new S1. S2 is now going to be the center of these 3 points, S2. And S4 is going to stay in this same spot, S4. Okay? So I'm getting a little bit closer to what I think is a stable configuration. Now, I think S2 moved the most here, right? This was probably the most consequential thing. So what's going to happen is I'm going to get a new Voronoi diagram now. See, S2 and S3, S1 and S2 look like this. Something like that. And then S2 and S4 looks like something like this. Okay, so now I can assign these points, and I'm going to update the centers one more time. S1 is now going to be over here. S1 is now going to be in the center of this clump. S3 is going to stay in the same spot. S2 is going to center a little bit over here. And S4 is going to be, this is S4 in this spot again. Okay, and now I'm going to get Voronoi diagram, which will be slightly shifted over here, but is basically going to be stable. At this point, I'm going to stop, right? All the points are basically assigned to the same center they were in the previous step, but I had updated the placement of the centers here. Okay, so this is kind of, it's this iterative process where these centers slowly are moving, hopefully, towards the center of their groups of points, and then when a site loses a bunch of centers on one side, it shifts away from it towards kind of where the center or the average of the rest of its points are. Okay, and so it slowly converges in this way. Okay, right, so if you go back and look at this again, there are the two steps. There's the, if we think of this one as the A step, this is the assignment, and this is where I'm doing this Voronoi diagram, right? So the Voronoi diagram is with step A, where I'm doing the assignment, and that partitions the points into these sets, right? And then there's this step B here, where I do a recenter, and that's by doing this average of these points, right? So the reason why this works and this relies and assumes that I'm using the Euclidean distances and my centers can be everywhere is because this step here, I can take this average, and this is kind of locally optimal, right? Given that partition of the points into these sets, right? Then this is the best place to put this site. The representative point for that set is going to be the average. We talked about why that was a bit on Wednesday, but because that's the optimum, that means that I can do this step. And the first step, the reassignment step, is kind of implicit in the way I've defined this cost function. Okay, so question. So if we wanted to separate what seems to be two groups on the right, okay, we would have to decide on 5 initial points. Okay, yeah, so one question is, how many different clusters did I want? I said K was part of the input. If I wanted to separate these two sites on the right, S4 is they're kind of these two groups of points here, right? And S4 has kind of, there's the top part and the bottom part. I could think of those being two separate clusters, but I've assigned one site to represent both of them. I would probably guess that if K was given to me, that this is probably the optimal configuration that I found. Okay, and so if I wanted to split those two sets further, I drew them like this on purpose so someone would ask this question, so great, yeah, I would probably need a 5th site, although that's not always true, right? It could be that I could separate these with 4 sites, but then I would only have 2 sites for the other 20 or so points, right? I have 20 points on the left, and I don't want to draw too much on here because it's already kind of cluttered. But if I have 2 sites left on the left, I might find an optimal configuration. Let's say that I had 1 center here and 1 here, right? So, and then two sites on the right. That might be a local optimal solution. Okay, let me try and draw another example that might make this more clear. Okay, so let's say I've got, and I'll try and make these as tighter clusters. So this is maybe more obvious what's going on here. Okay, so let's say I've got these points here, and I say K is equal to 4. Now, probably the optimal S1, S2, S3, S4 is going to be like this. Okay, but let's say I have a suboptimal. I'll call this T just so these are different. I could have used a prime, but this is a little bit less kind of messy. I could have said this is T1, this is T2, this is T3, and this is T4. Okay, let's draw the Voronoi diagram here. I'm going to get for these sites. Okay, so this is the Voronoi diagram for the suboptimal set of the sites T. It's stable. I'm not going to update. If I start in this configuration or if I get in this configuration after some number of steps, the algorithm is not going to move, right? So Lloyd's algorithm is stuck, right? So Lloyd's algorithm will get stuck in this configuration here. And if I know I want K sites, then this is it's going to be kind of stuck in this way, right? There's no way it can move from this. If I update the location of the sites, well, they're going to be exactly where they are. These are always already the average of these clusters. And if I update the assignment, well, they're already assigned to the site that they're assigned to. So that's not going to update it either, right? So Lloyd's algorithm is, in this situation, will get stuck and it's not going to get the right answer. If you look, this is pretty much kind of the same configuration as over here. I redrew it so that clusters are a bit tighter so you could see what's going on a bit better, but it's probably not the right answer. And this is a shortcoming of Lloyd's algorithm in that way. It seems like it's a very natural thing to do once you see it, right? You assign everything to the closest point. Given that assignment, you take the kind of, you average things to get to the kind of the optimal point given that assignment, and you just iterate on this. This idea of iterating between two steps where you know each one is helping is actually quite common in a lot of these more complex formulations. But it's much harder to show that, and in a lot of cases, you can't show that you're going to get the optimal solution, right? With gradient descent, when the function is convex, we could guarantee an optimal solution. And with the power method, it turns out that the constraint space we have of having unit vectors is not a convex space. So we can't use gradient descent logic to show that this is also going to converge, but you can show through these other methods that I went through in class that will converge. For Lloyd's algorithm and kMeans clustering, we do not have that luxury. We can get stuck in these local minimum. And that's because this is a way of, you can conceptually think, if I have a cost function, right, I could think of this as a gradient descent algorithm in some ways. I'm not explicitly computing the gradient, but I'm doing something kind of like that. And you think of, okay, if I have four sites, each of them has two coordinates, it's kind of like an 8-dimensional space, right? Each site has 4 coordinates. And so that's 2 times 4 is 8 dimensions. I think of trying to find the minimum in that space, right? That minimizes the associated cost function. I could write it down as that formulation, and then I could try and run gradient descent on that. But that is not a convex problem, because this is an example of a local minimum. If you have a local minimum that's not the global minimum, it's not a convex problem. And this is the reason why people use this algorithm, and there are lots of other variants, but they're much more complicated. So that's why people use this kind of simpler idea. Okay, most of the time this works pretty well. Okay, so I'll say most of the time Lloyd's works well. Okay, I'll say with so with a little help. Okay, there are a couple of tricks you can do that will help Lloyd's out and will help it get out some kind of strange cases that have. And so, you know, I've asked you to implement a number of things in this course. I'm not going to ask you to implement this because there are a couple of like weird corner cases you have to deal with, and it's kind of a painful and sort of the end of the semester. So I'm not going to ask you to implement this. If you take the data mining class, you'll probably implement it. Okay, so a couple of tricks, kind of tricks to help Lloyd's. Okay, first one, we'll say random. So random restarts. Okay, so what do I mean by by random restarts? Okay, I'm going to I'm going to randomly initialize S. Okay, so I'm going to randomly initialize the starting set of sites. I'm going to run Lloyd's, and then kind of compute the cost, right? Remember, I had this cost function, the sum of the squared errors, this sum of squared errors. Okay, and then see, repeat A, B, say 10 times, and then D, return final S with the lowest cost. Okay, so I'm going to right. So think of, you know, you'll run it with an initial random guess, right? Initially, I chose in these 4 points here, and that was maybe at random, and I got to this configuration. If I chose a different 4 sites, I might get to the same configuration. A lot of times you will, but sometimes you'll get to something different, and that might be better, right? So if you don't know any better, you can run this a bunch of times, and if it seems like it's fairly stable, then that's good. I can stop. If I'm getting a lot of variation, I might keep running until I keep getting a low cost over and over again, or I might just say I'm going to run it for 10 times, right? And this will help me often get to the right right solution. Not always. It's not guaranteed. In fact, there are some configurations of initial input where, with very high probability, you're going to get to a suboptimal location. And people have kind of investigated this probably more than you would want people to spend time on this, but you know, and it's very interesting initially to study this, certainly. And so there have been better ways to initialize. Okay, and so there are a couple of other algorithms that we discuss in the book. I'm not going to go through this in this class. One is Gonzalez algorithm, which is a deterministic algorithm. It's not randomized, so I can't run it more than once, but it will guarantee that the centers are spread far apart. Okay, and then there's a kind of a randomized version of this called kMeans++. Okay, and so this was actually invented by a couple of friends of mine when I was in grad school. They were at Stanford. But so this is not too old, but now it's built into like even MATLAB and all over the place. And this is a better kind of a randomized way to initialize the starting configuration. And it's randomized, so you can still use it with the random restarts. but it kind of guarantees probabilistically that the points are spread out, and it's randomized. So sometimes it might not work, but if you run this enough times, it's kind of, with any arbitrary setup, it's guaranteed to do fairly well, to get fairly close to the right answer. The guarantees are kind of like an 8 approximation or something, but in practice, it generally works very well. You might repeat it like 5 to 8 times. And so I think if you run kMeans plus kMeans in a lot of different libraries, it depends on which library you use, they will initialize with kMeans plus plus and run a few times and give you the best answer. Some combination of this. So there are a couple of other, so these are the kind of the main things you would do to kind of improve Lloyd's algorithm. And with this, it actually works fairly consistently pretty well. You know, not always kind of the strongest possible guarantees that you can get with something like power method or a lot of the gradient descent, especially when you have kind of a strongly convex cost function. But this works fairly well. Fairly simple algorithm, but you need to add these kind of these tricks to help it along the way. Well, as I'm here, I want to mention a couple of corner cases, or as long as, so you're here, I guess I'm here all day. So a couple of corner cases. There could be and this is why I might not have you implement in this class. There might be a site with no points so closest to it. Okay, so you might get into a configuration where I've got a set of points here, set of points here, right? And I end up in a case where, let's say I'm going to have sites that end up looking like this somehow. So I have S1, S2, S3, S4. And so if I look at the Voronoi diagram here, like this, there are no points assigned to S4, even though maybe it looks like there are kind of 4 clusters, but S3 took both of them, right? What do I do in this case? I would, so you have to write a sanity check for this in your code. Otherwise, you're going to divide by 0 and all sorts of weird stuff happens, right? So in this case, randomly assign S4 with no points in X4 to some xi in X, right? So if I randomly assigned it here, then great. Then S4 and S3 will kind of shift apart, and they'll capture those clusters. But if I assigned it, say, up here, probably what's going to happen then is S1 and S4 will split that cluster, and so and S2 will stay in the same spot, and S3 will stay in the same spot, and I'll get stuck in a in a local minimum, right? So a common trick is to say, so from xj with the most variance, right? So I want to find the one that has the most variance here, right? So this cluster, these distances are much larger than these distances here. Okay, so I would probably assign it to somewhere in this cluster, and then it would split that cluster, and I reduce the overall variance. So that's probably good here. Okay, so there are a bunch of these little tricks like this that you need to kind of do it to work very well in general. Okay, so this is also a point where I want to say that everything looks pretty clear when you look at this in 2 dimensions, and when I've drawn stuff like these blobs. Okay, so in most data, I want to say, looks like you know, it's going to look like this. It's actually going to be much higher dimensions. This is actually RD, and my data is going to look like. So it's very common. I've seen lots of data sets where people try and plot this and say, I've tried to run clustering on here, and the data looks like this. I say, I've run clustering on here, and I got back some answer that looked kind of like this. And they say, is this a good clustering? And I say, yeah, no, you know, we'll do PCA, right, to draw this in 2 dimensions. And we'll kind of look at the assignment. Sometimes the clusters will even overlap with each other when I've drawn them in PCA. And I can't really see what's going on. And I don't know if it's a good clustering or not, just by looking at this, but probably not, right? I'm not seeing these separations. So this one has like no, so blobs, right? Usually you want to cluster data when it has blobs. Right, I showed you this demo in Python before where there was this make blobs kind of function that made blobs just so you could run clustering, so clustering would work like you'd expect it to. Data does not always look like that, right? So if you run Lloyd's algorithm on this, okay, I've divided the points into some kind of into these regions that are closer to each other. Right, and there's some Voronoi diagrams you can draw to kind of understand this, but really they're high dimensional Voronoi diagrams. So they don't actually look like this. There's actually, you know, these 2 clusters might actually be closer to each other than the other 2. But so there's some kind of weird stuff going on. I would call this a smear, like if you're smearing some cream cheese on a bagel, kind of you get a big glump in the corner and then you spread it out. A lot of data looks like that, and it doesn't naturally have clusters. It might if you choose a different way to define the distance, but if you use Euclidean distance, it might look like this. Maybe there's a different featureization, a different distance function where there are clusters, but in this one there isn't. And so you should be aware that it's not always going to look like these nice pictures I'm drawing for you, okay? But clustering is like a major topic. People want to apply it all the time. I've seen a bunch of, not a bunch, but a couple of like talks from venture capitalists or CEOs of companies said, we ran clustering and it perfectly separated our customers into different classes where we know this customer likes this and this one likes this. And it's usually not that. It's usually more of a continuum. And that's something where something like dimensional reduction that reduces the kind of the subspace describing the model parameters might be more useful than clustering. And so these are, the difference between these is often confused. Now, clustering does come up. Sometimes the data is going to look like one of these pictures. And then you do want to run clustering because it really nicely determines, kind of separates them into these groups. That's really cool, right? But don't believe that clustering always works. Okay, so that's the warning. And if it doesn't work, it's oftentimes it's because you know, maybe you've chosen the wrong distance function. Okay, I want to talk about 2 more things, and so I will kind of order them by what I think is more practically important, because we have 10 minutes left before the quiz. The first is the number of clusters. You know, number of people have asked, how do I choose the value k? It's a great question. So yeah, so you know, often it's given to you as input, but if not, what are you supposed to do? And so I think the right way to think about this is to draw a plot and to write some cost function, x of s, right? Remember, and the cost function that we're trying to minimize is going to be, remember, is sum of I equals n times xi minus phi of s xi squared, right? So we have this cost function, and what's going to happen to this cost function as I increase k? There's only one thing, like I can run this algorithm, right? So I run with k equals to 1, right? We know that's just taking the mean of the set of points, and I can measure this cost function. I'm going to have some value here, right? And then I'm going to run it with 2, k equals 2, and maybe I'm going to get a different value like this. In general, what is going to happen as k increases? This is kind of like the overfitting problem, in that as I increase the degree of a polynomial in regression, the cost, the sum of the residuals, keeps going down, right? And as I put higher and higher degree of a polynomial, I can fit it exactly. Eventually my cost is 0. So if k equals n, then this cost is exactly 0. It's going to be exactly 0 when I have the same number of clusters as I have data points, right? I assign 1 data point to each cluster. That's it. I'm done, right? So, and in general, this is always going to decrease. And so what it's going to look like is often like this, where it's going to be decreasing, right? So I have a value k equals 2, k equals 3, k equals 4, you know, where this is k equals 2, k equals 3, k equals 4, k equals 5, okay? And so the more clusters I have, I'm going to have a lower cost, but that doesn't mean that's better, right? Because I don't want every point in its own cluster, probably. This is often called, so this is often called like an elbow plot. Okay, you could think of it as like someone's arm. All right, so I've got someone's arm coming down here, pretty long arm, and then I've got the elbow, and then their hand on the end here, right? And so what I want to do is I want to identify this elbow, okay? And I want to choose k here. And in this case, equals 4 or 5, right? So it's, you kind of want to wait till it flattens out, okay? And if you do have a bunch of blobs, at some point it's going to kind of flatten out, separating a cluster into, I can always separate a cluster into more pieces, but it's not going to decrease the sum of squared errors by too much anymore. Where if I do have 2 separate clusters, and they were in the same one, and then I separated them, I'm going to decrease the cost function a lot. Now I'm always going to start to get some sort of diminishing, some sort of diminishing returns where the cost is going to stop going down. It's going to keep going down a little bit, but not by very much at all, right? And you kind of want to identify where it flattens out. So where it flattens out. Okay, that's where this elbow kind of is, and that's kind of how you would choose k. Okay, there's not a lot of science to it. I've got this picture of an elbow on an arm drawn there, but you know, this guy, you've used the elbow method, so he's happy. All right. Okay, so because you've identified his elbow. I want to say that if you have a smear, so this is the case with a smear, the cost function is going to look fairly similar. Okay, so this is probably the cost function with clusters. This is with clusters and this is with a smear, it's still going to be kind of decreasing. I'm going to even make this, it's still going to even come down. There's still going to be some diminishing returns here, but these are going to look kind of quite similar. It's going to be hard to tell these apart. I plotted, well, I don't know if it's in the version of the book that you guys have. Hopefully it is, but the difference is not too big. So it's kind of, it looks like, okay, this makes a lot of sense. I'll be able to use this, but if you plot it for data that has one cluster, it's still going to kind of look like it kind of has an elbow, kind of a resting elbow, not like a flat elbow. And so the difference is not going to be too big. And so it's still kind of a black art to actually use this technique. Okay, but if you're going to do it, this is about as, basically the best technique I know. There are other kind of statistical ways we can talk about in the context of mixture of Gaussians, maybe a little bit in the next lecture, but it's not going to be terribly too different from this. Maybe a slightly different cost function you can put on here. I'm not sure I trust that any more than I trust this kind of hand wavy technique with the elbow. I guess technically, if it's an elbow plot, the hand isn't waving, so that's good. A hand wavy approach is usually one that's not well founded by mathematics, which is what this course is supposed to be about. Okay, let me quickly say I've got 3 minutes left. So y converges. Okay, so let me just say this quite quickly. So remember we have this cost function, right, which is going to be, I'm going to write this two ways, where this is going to be x minus phi of s x squared, and I can also write it like Sj and S, X and X and Xj. Okay, I can think of it as these two different ways here, where one, I've just rewritten the sum, so this internal sum here is only over the points within one of the clusters, okay? And the key insight into why that this converges, why Lloyd's algorithm converges. Yep, so I think I've got 2 minutes left. Okay, why Lloyd's algorithm converges? It's doing these two steps. And both steps, A and B, the assignment step and the centering, this is step A, this is step B, right? Step A you can see as minimizing. These are equivalent cost functions, but this is step A is definitely minimizing this first formulation. I'm choosing S to minimize the cost. And step B is minimizing this second formulation, because once I fix the set of centers, right? Once I fix the assignments, right? This is basically giving me the assignments here. Once I fix this internal sum, I've got k terms inside these blue brackets. Each term is minimized by the choice, right? This one is minimized by the choice of S, right? And this one is minimized by this mapping function, right? So I'm just kind of, each one is minimized the same cost function. So if the cost function is decreasing, I can't get in a loop or get in an infinite loop in here. Otherwise, I might get an infinite loop somehow. But if the cost function is going down, then I can't return to any configuration I was at before, because that would have meant the cost function was flat, right? It would have gone down and then back up again, which I know can't happen because each step is minimizing this cost function. Okay, and this is kind of a key insight to realize why it's converging, even if it's not a global minimum it's converging to. Okay, great. So I will stop here and open up the quiz. I will, or the quiz is automatically open, but I'll stop the lecture here. You guys can go and start the quiz. I'll be online for questions about the quiz for the next hour until 3:30, and then I think Hassan will be, trying to check emails while I'm in some other meetings. But I'll be trying to answer stuff that comes up during the quiz as I can do that. Okay, so yeah, go ahead and start the quiz. We'll talk a little bit more about clustering with a more statistical formulation and some other variants on the next lecture on Wednesday.